Alright, before we start looking at this video, you need to watch the non-camel video. It is an excellent video with great graphics and can do a much better job of explaining the phenomenon rather than me blah blah blahing on the board. So watch that. It's a woman who talks very fast, but she's amazing. So you're going to have to stop it if it's going too fast, you're not comprehending it. You find your eyes glazing over, stop it, back it up a bit, and then continue on. It is an amazing video. Take notes while you do it. Okay? If you haven't done that, stop it now, stop this now, and go back and look at that. And then we'll continue from here. Okay. What we're basically looking at here are the harmonics. Now, there is a pattern of waves that overlap each other, and they follow a mathematical pattern as was shown in the video. So there's two basic scenarios: one with a string instrument and one with a closed-end pipes. Now they do exactly the same thing. They have the same mathematical formulas. The different mathematical formula is the open closed-end pipe, which we also call an open pipe. We call this a closed pipe. And of course, like I said, this is the string instrument. Okay, and I've listed that up here. Okay, so let's take a look at the mathematics for this. First of all, we're talking about fundamentals, and as she described it, the harmonics are also called overtones. So we're looking at the overtones. So for the two closed ends with a string instrument, which is also the same as the two open end pipes, you have a series of wavelengths associated with the length of the string, and it goes up by half of a factor each time. So the mathematical formula for that is that the length of the string, or the pipe, in the case of the pipe, is going to be n over 2 times the fundamental unit. The fundamental unit is the wavelength sub 1, also known as the fundamental frequency when we find the frequency based upon that. Fancy that. We have the formula for that. We know that frequency can be calculated by taking velocity over the wavelength. So since the length is equal to 1/2 the wavelength, then that means the wavelength is twice the length of the string. So whatever string or pipe you have, the wavelength in a fundamental is going to be twice as long. So this is V over 2L for the fundamental. Most of the calculations will be done with the fundamental. It would be silly to do otherwise. So the general formula here is f of n, where n is 1, 2, 3, 4, and so on, is equal to the velocity over the wavelength of whatever harmonic or overtone you're looking at. And then we can rewrite that, that the frequency of a particular fundamental, n, first, second, third, fourth, whatever, is just that n value times the fundamental frequency. And then that can be, since frequency is defined as V over 2L, we can substitute that in. And like I said, this applies to open pipes. Now, mathematically, here's an example. What are the first 4 harmonics of an open pipe whose fundamental is 135 hertz? Well, this is pretty simple, because we just go 1, 2, 3, 4, which is what happens for both the string instruments and the open pipes. So we're going to get answers of 135, 270, 405, and 540 hertz. If you have all 4 of those frequencies occurring at once, it's going to sound nice and in sync. And it's going to be a much fuller sound if you include all that rather than just one. Open pipes are a little bit different, as they show, because of how they only have 1/4 of a wavelength with the length of the pipe. And so this now becomes lambda 1 over 4 as our fundamental. That is our main one, our fundamental. But because of the fact that you don't get complete nodes in your waves, then you have some residue here, and that's why we get these fractions here, as she showed. So you have 3/4 of lambda, 5/4 of lambda, and m over 4 times lambda m over lambda m. Only m. Now m is odd numbers. There are no even numbered values for that. 1, 3, 5, and 7. And therefore, then the formulas we use are going to be slightly different, but majorly different, because of the 4 instead of the 2 here, and the fact that we never use even numbers for this. So keep those handy. Example of what we would use here: what are the first 3 fundamental frequencies of a closed pipe that has a frequency of 180 hertz? Well, the first fundamental, the first frequency, which is the fundamental, the first harmonic, is going to be 180 hertz because it's 1 times that. But the second one is going to be 3 times that, which would be 540, and the third one would be the fifth harmonic, which would be 5 times 180, which is 900 hertz. So be careful of that. Example: if the length of the pipe is 45 centimeters, what is the wavelength at 333 meters per second for the speed of sound? So, since we're trying to find wavelength, we know L equals lambda 1 over 4, therefore lambda 1, the fundamental, is going to be 4L. So it's 4 times the length of the pipe. The pipe here is 45 centimeters, but we need to change it over to meters. We get 0.45 meters, and our answer is 1.80 meters. Now, related to that, this is what is the frequency of the fundamental under these conditions. In which case, you're going to take the velocity for this, which is 333 meters per second, divided by, and this is the first one we're going to do. There's no sense in doing the others, but we're going to take the fundamental wavelength here that we calculated, 1.80 meters, divide those two, multiply by 1, and you get 185 hertz. So that is the tone. And there are other factors involved in making pipes. This is not the only thing. You can also have the diameter of the pipe is also something that plays into it. And actually the material that you make the pipe out of, how it vibrates, is also something that many take into consideration. We're not going to look at those factors. We're just going to go with the basic fundamentals and part of the pun of harmonics. So, your practice problems are at the end of the script. Have fun.